In this webinar, we're going to be giving you an introduction to integrated catchment modelling, and the presentation will focus on the innovative product called InfoWorks ICM. Now, the premise for this particular webinar is there are a number of government directives that have come out over recent years that instruct utility companies and cities who are responsible for drainage assets on how they should control those assets, how they should manage those assets, and particularly that they need to understand how those assets perform, both when conditions are normal and when conditions are abnormal. And modelling has become a prerequisite for that understanding, and with modelling we can really understand the impact of developments in the urban environment and indeed in the rural environment as well. As a couple of examples of the government directives that have been given to utility companies over the years, we have here on the screen a couple of pictures from the Surface Water Management Plan Technical Guidance issued by the UK government in March 2010, and also the River Basin Management Plans that have been issued by the European Union as part of the Framework Directives in 2000. These are classic documents. There are of course others from around the world, but this is very much indicative of governments beginning to take a much stronger stance with utility companies and with cities to understand how their assets work. Now, if we think about the sort of incidents that can happen with urban drainage systems and with river systems, then we can start to think about what we need to do to understand what is going on in terms of the holistic picture and all of the sources that are contributing to flood events. On the screen you can see some example pictures. These are classic situations where we have flooding or inundation in urban and rural environments. Let's take as an example the picture on the top left. Here we can see the classic example where there's been a short, sharp storm, perhaps a summer storm. The rainfall has been quite intense for a short period of time, and the gullies on the road are unable to accept the flow from the system, so water ends up ponding on the roadways. That in itself is not necessarily a problem. Vehicles do tend to drive through floodwaters at speed, and that can create a bow wave which in itself can impact on properties, but generally speaking stormwater in roads is more of an inconvenience than anything else. However, if we take the other example, top right in this particular case, here is a sanitary overflow which is happening in a parkland area. Just to the left of the overflow we can see a roadway where people jog and where cyclists exercise, and obviously a sanitary discharge going off at that location is, well, at the least unpleasant and potentially at the worst a potential danger to human life. So we need to tackle those sort of events, and there are lots of different sources that contribute to those events, but rainfall is typically a big influence. If we take the example of the pictures on the bottom there, particularly on the bottom right to start with, here we can see inundation in a large city. That type of event is typically caused by a catastrophic failure of, say, a reservoir or a dam, or perhaps a breach in sea defences, letting the sea come in and flood the city. And those are, that's on a huge scale, and it's a much bigger issue than the sort of localised flooding events that we looked at in the first two pictures. On the final picture we can see a car park. It's obviously raining hard, there's a large amount of runoff being generated in that car park, and the runoff is running over land through the gap in the stone wall and able to discharge into the nearby watercourse. And in essence it would first appear perhaps that is a situation which, while undesirable, is actually being remedied by virtue of the overland flow into the watercourse. However, you do have to bear in mind that that is a car park, and the cars that park there, particularly during dry weather, will likely drop oil and other pollutants onto the surface, and they will stay there until such time as there's an intense rainfall storm, and then those pollutants will be picked up in the wash-off and will be washed into the local watercourse, causing a pollution event, and that is a direct side effect of the flooding situation which happens first. So these are all very different sources of flooding, and they all have quite different impacts. And traditionally in the past, these four different scenarios would have been modelled by perhaps four different software applications. A stormwater model for the flooding on the road, a wastewater model for the sanitary and or combined system failures, perhaps a river model, or a sea-based model looking at the mass inundation of the city, and perhaps a pollution model looking at the pollution event. With hindsight, perhaps a single fully integrated model for the whole catchment would be a much better plan. And that is essentially what we have with InfoWorks ICM. It's just one application, and it's able to deal with all of those different scenarios very simply and very easily. So let's think now about some of the techniques and some of the applications that we need to do when understanding the interactions between our drainage network, perhaps local watercourses, major rivers, and the urban environment and the rural environment in which those networks exist. If we think about how we've done things in the past, and particularly taking the snapshot on the left-hand side of the screen, this is a classic urban model with a degree of street flooding. So similar to the picture we saw on the previous slide. We can see that the rainfall has generated a significant amount of runoff, and a lot of that runoff isn't able to enter the underground network and instead is actually forming flooding on the surface, and it's been captured by the roadway in this particular case, which is for the most part transmitting the water down the road. However, as you can see from the screenshot, there are a number of buildings, houses, properties and shops which are either side of that road, and they will be inundated by floodwater should there be a large amount of rainfall runoff generated on that particular catchment. So the stormwater models will be used to show where that street flooding is, and perhaps more importantly, the properties that are likely to be impacted by any such flooding. Now that's in the urban area, and that's a quite classic scenario. But we also can have the perhaps bigger scale flooding situations which occur when rivers are involved in the overall problem. So the other screenshot on the right hand side of the screen, we have a classic river with a horseshoe bend in it. There's a large area of the floodplain which we can see to the left hand side of the river there, and that floodplain is fully inundated, and it's storing a large amount of the excess flow that can't currently be handled by the river system. But there is so much flow that the floodplain itself is actually over capacity, and some of the water from that river has actually gone into the urban area which is within that horseshoe shape. And we can see on the second panel of that particular screenshot where the river water is travelling within the urban area, and we have some little red velocity arrows which are actually showing the areas where there are significant velocities of river water travelling in that urban environment. So again, we have a numerical model, in this case a river model, and we're using it to look at the prediction of inundation and the overland flow routes. And those are traditionally been done as two separate applications, as I said. The Holy Grail, what we really want to do is to say, no, we don't want to do that as independent models. We want to do that as one integrated catchment model, because it's very likely that any rising river levels are going to impact discharges from stormwater networks, and if the stormwater network is impacted by the river, it will likely discharge to the surface as well. So we do have these interactions, and the only way we can fully establish what they are is to use one fully integrated catchment model. And that is essentially what InfoWorks ICM brings to the table. It integrates both the rural and the urban environment and all of the drainage that can happen in those two different types of catchment. And the way we do that at a mathematical level is to integrate two types of mathematics, both what we call one-dimensional mathematics and two-dimensional mathematics. The subtle difference between those two approaches is that within one-dimensional mathematics, we don't have to worry about the direction that the water is taking. And that's because the water is typically travelling in a pipe or travelling in an open channel, and it's that pipe or that channel that will dictate where the water goes from A to B. It can't really go anywhere else once it's in that container. However, once it leaves that container, once it leaves the pipe or leaves the channel, and typically will exit onto the surface of a catchment, once the water is on the surface, there is very much a directional component that needs to be taken into account. The water will travel over land, it will be driven by gravity and by the different terrain on the catchment. And to model the flows travelling over land, we need two-dimensional mathematics. But just as with the real catchment, those one-dimensional and two-dimensional aspects can't exist in isolation. They have to interact with each other. Water will exit from the sewer network or the river system onto the ground. It may well travel from the ground back into the sewer network or into the river system. So the one-dimensional and two-dimensional mathematics need to talk to each other. to represent what actually happens in the real world. And InfoWorks ICM really is the first software application in the world to successfully combine the one-dimensional and the two-dimensional mathematics and put them together so that we can have one application which has one simulation engine that looks at the catchment as a whole and can look at all aspects of drainage on that catchment. Now, I want to show you a couple of examples now of InfoWorks ICM in action. These are animations. This is not the real software. We'll come to that in just a short while. But I really want to show you some of the work that Innovyze have to do in the background before a software even comes to market in order to check that the theory can in fact be put into practice, and indeed can be put into practice in a format that is commercially viable for commercial hydraulic modelling, so that consultancies and utilities can do this sort of work and essentially do it commercially profitably as well. So, two examples I'm going to start with. The first example on the left hand side of the screen is not a real model at all. This is a prototype which our development team put together in order to check that we could in fact integrate the one-dimensional and two-dimensional mathematics, and that we could produce one model which had all aspects of the catchment in it, and all those different aspects would interact with each other during a storm event. So as a description of what we have the river system, which is represented by this shape running through the centre of the model that we can see here, and this will represent the river. We then also have in the top half of the screenshot this area which represents the urban catchment. The blue polygons are representing the houses, the grey shapes are representing some simple roadways, and we have some green dots which represent the manholes and where they're located within the urban catchment. Under the ground there are pipes which are connected up to these manholes, and those pipes run down and essentially discharge the stormwater into the local river. Over the catchment as the whole, you can see there is this spider web now. This is actually what we call a 2D mesh. So this is our mathematical blanket, which is a exact representation of the underlying LiDAR data, which is actually providing the slopes changes on the terrain and on the ground. And everything here is all linked up in our one integrated catchment model. So this is a recording of the results that are produced. So here is the rainfall happening on the catchment. Rainfall happens very quickly. The urban area experiences a degree of inundation, some localized flooding in this area of the catchment, but most of the other houses are not impacted by that. Meanwhile, as time goes by, the river system fills up, and in fact fills up to such an extent that the river goes over capacity, and we have the storage taken up in the floodplain. Once that floodplain storage is over capacity, the river water will escape on the other side of the bank, comes up and inundates the local town, which we can see here. So now these properties are actually experiencing a degree of stormwater and also river water going into the buildings, and in fact going also into the catchment, and river water is entering these manholes that we have here. Once it's entered the manholes, it's travelling down the system, and river water has been ejected by this manhole here because the exit of the stormwater network into the river is blocked by the fact we have high water levels in the river. So water can't come out here, so it's actually forced out of this manhole. And so this discharge that we see on the surface here is in fact river water, which was initially transmitted through the sewer network and then moved back onto the ground. Now, this is very quickly what all of the typical interactions are in an integrated catchment model. And so we have this prototype model which is proving beyond any doubt that we can integrate our river systems and our sewer systems and have all the hydraulic interactions happening. As I said, that's not a real model. That was very much a prototype, a proof of concept that we put together to ensure that what we were trying to achieve with InfoWorks ICM was in fact possible. On the right hand side of the screen we have a real model. This is a model actually in the north of Wales, up on the North Wales coastline, in the area looked after by Conway Council, and this is a real life situation which actually is very close to the prototype that we've just looked at just now. In Wales they're located on the west half of the United Kingdom. There are a lot of mountainous areas, a lot of very steep hills, and that area of the UK also experiences a high degree of rainfall as storms travel across the Atlantic and do landfall first in Ireland and then in Wales. And it's the mountains that will actually take the majority of the initial rainfall as the storms travel across the United Kingdom. And that water will then travel down this steep hillside that we can see here. This is a very steep hill down to where the town and the village is located at the bottom of the hill, which is classically where these sort of locations occur. When that water does come down the hill, it is picked up and captured by the stormwater network that is there to provide drainage for the local community. And we can see at the moment these green manholes represent those inlets to the stormwater network. And under normal conditions, that network works absolutely fine. However, in degrees of high rainfall, the manholes here will start to lose water to the surface, and we'll start to see localized flooding in this area here. There are some reliefs in the along the side of the road here that will allow any excess rainfall into this area of the catchment, so that we can keep the inundation in the roadways and near the properties to a minimum. So let's have a look at what happens when the rainfall hits the catchment and we start to produce the degrees of runoff. Initially everything is absolutely fine, but after a short while we actually start to see the flooding occurring, just localized street flooding happening in these areas, and some of that water is allowed to escape into this area in order to minimize the risk to properties. So initially you might think that the network is actually performing quite well. However, as time goes on, the river system starts to fill up. The natural floodplain storage is taken up initially, but if the river levels keep rising, the banks, the protection banks that have been built here, are overtopped, and river water starts to come into this area here. And once that happens, that river water can actually find its way back through the storm relief and into the roadways. And in fact we now get a high degree of flooding happening in the village at this particular point here, and these properties, which initially just had a small amount of stormwater inundation, are now experience a significant amount of river flooding as a result of the existing storage areas being unable to contain those flows. So as I said, this is a real model, and this in fact was one of the very first ever fully integrated catchment models that was built and utilised in the United Kingdom. So let's at this point take a break and summarise what we've been discussing so far. First of all, to produce an integrated catchment model, you need to be able to fully integrate the one-dimensional and the two-dimensional mathematical techniques that are needed to look at all aspects of the catchment. Once you have that 1D, 2D integration, you can look at what's going on below the ground in your pipe networks, in your river systems, as well as what is happening above the ground, so surface flows that are travelling over the catchment. And with InfoWorks ICM, all of that can be put together really as never been possible before. Once you put everything together, your hydraulics and your hydrology of the catchment all become one. So whether it's a natural catchment or a man-made catchment, all the interactions are there, and all those interactions can be incorporated in one mathematical model. And what that brings to the table is an ability to really fully understand all of the interactions that are happening on the catchment. All the processes over every part of the whole model can be taken into account. And what that provides is a relatively simple way, but certainly a very cost-effective solution to what can be a very difficult and complex engineering challenge. The challenge is still complex, but we can simplify it in terms of our modelling approach by just having one application that can look at all of these different things going on the catchment at any particular given time. Okay, so that's the theory behind what's happening, and that was a quick look at some example catchments. What I'm going to do now is to move on and give you a live presentation of InfoWorks ICM, where we're going to look at some real catchments of different types, of 1D catchments, of 2D catchments, and see what's going on. So let's change from the current presentation and actually go into the software itself. So here is InfoWorks ICM. So this is the real life software now. We have a master database over on the left hand side of the screen here, and this has a number of example models which we're going to look at for the next 20 minutes or so. Let's start with something pretty traditional and pretty straightforward, and this is the classic 1D model. So this is your type of drainage model that's been produced probably for the last 15 or even 20 years. These are models that are classically used to look at stormwater flooding or to look at wastewater flooding. We're not particularly interested in surface flows at this particular point. We're just looking at the operation and performance of the model itself and of the catchment and the discharges from the system. This is a coastal catchment. It's actually located in the north of Scotland, and the discharges in this particular case go into the North Sea, which is located here. You can see on the diagram we have the green dots, again representing our manholes, which at the moment are performing correctly. Under the ground, the pipework links up those particular manholes, and above ground we are representing our properties shown by the red polygons, and we also have GIS layers in the background which allow us to look at a general outline of the catchment, so the sea in this particular area and the urban area that we have here. Now this background mapping is typically produced and provided by GIS systems, so Esri's ArcGIS or the MapInfo product from MapInfo Corporation. And that's traditionally the way we've been working with mapping for many, many years now. But one recent development is the introduction of open web map services. So web map services are WMS, and they are provided by the likes of Google, but also organizations like OpenStreetMap and indeed many others as well. And all of those mapping scenarios can in fact be utilized by InfoWorks in addition to the standard GIS mapping. So here I have an example of OpenStreetMap, which is a web map service, as I said, and we can have a look at the properties of this particular layer, and we can see that this is its web URL, and as long as you know the web URL for your map service, then you can apply it in InfoWorks ICM. So if I drag out that web map service into the background of my model, my GIS layers will be replaced by the open web map service from OpenStreetMap. And here we can now see the sea, we can see the blue colour representing the sea, we can see the urban area, we can see the roadways, and we can see where all the other green areas are as well. We don't have to have just one or the other. We can mix our web map services with our standard Esri or MapInfo GIS layers. And when we bring both together, then we can overlay our mapping data with our GIS sources and put the two together and produce a much better picture. Why do we want to do that? Well, because when we can put everything into perspective, when we then also apply our hydraulic results, as we've done here, we can see where the system is experiencing a degree of failure. So that's these 4 concentric circles that are shown here, plus a 5th slightly smaller event over on the right hand side. So we can see precisely where the sewer network is not performing correctly, and we can see the relative impacts of that on the urban environment. So anybody living in these locations is likely to see a degree of network failure here with stormwater or perhaps wastewater, if it was a wastewater system, exiting onto the ground at these particular locations. And that is traditionally what our 1D hydraulic models have always produced for us. They've been able to show us where a network is not performing correctly and where likely failure points are that would produce flooding to the surface. What the 1D models cannot do is show us what happens to that water once it's on the surface. And that's where we move away from the realms of 1D modelling and start to move into the 1D, 2D environment, where we can look at what's been happening in our basic system, as we've done before, but we can take a slightly more detailed view and look at also at what is happening above the ground. So here is another model. This model is actually in North London. Therefore it's the sort of property of Thames Water, so my thanks to Thames Water for allowing us to use this model for this particular webinar. But in this model we have both the classic underground network, which consists of our manholes and our pipes, which I think we can probably see here, but we've also introduced a 2D grid, which is this polygon over the top of the network with this spiderwork lattice that we can see in the background. Let's just momentarily turn that lattice off. And that really will show us the difference between a 1D model, which is what we're essentially looking at now, so that's our classic 1D model, and also what happens when we then convert it into a 2D model, which is essentially this addition of this extra area. Now, why is the 2D so important? Well, let's turn off that 2D zone again and just go back to make it a classic 1D model, and then do the same as we did before and say, well, let's overlay now the results of my model. And we can see here almost every single manhole in this model is experiencing a degree of failure for the simulation. So it has rained on the catchment and almost every single manhole is changed from the green, which would have been good, to either yellow, which is about to fail, or blue, I have failed, I'm actually losing water to the surface. What we can't see through any of that is where that water is going. We could probably make a guess that the water would be coming out onto the roads and the roads would be acting as carriers, but that's all it would be. It'd be a guess or an assumption. By introducing the 2D element to the software, we can change that assumption to being an actual result. So we'll turn the 2D mesh back on, and when we do that, the hydraulic results will be overlaid with that 2D mesh, and we will start to see where the water has travelled as it went over land. So let's just zoom in on the centre of the model to take a view of that, and we can see here that, as we might have predicted, the water for the most part is coming out of the manholes and being contained by the road, not only here but also in this area over here as well. However, where it's not able to be contained by the road, it's escaping, and it's actually then inundating some properties. So the properties that actually exist here, where the blue triangles are up against the properties, those properties are actually experiencing a degree of flooding from the roadway. Now, water typically will leave the roadways when the water depth exceeds the catchments or exceeds the height of the curbstones in that particular catchment. This being North London, a lot of the catchment is Victorian in nature, and the road curbs are actually quite high. They're actually higher than traditional road building would be today. But even so, there is a low spot at this particular point, probably because there's a drop curb perhaps put in so a vehicle can be parked in front of a house rather than in the road out front of the house. But unfortunately, if you put a drop curb in, not only will it allow vehicle access, it will also allow the water, and that's exactly what has happened here. So water is able to come up onto the pavements, it's able to get, in this case, between the properties and able to travel over land. There's a service road at the back of the houses with some garages. Those garages get inundated by the water as it travels over land, and it eventually ponds in this particular area here. Now, these houses are therefore also experiencing a degree of flooding, but not because of the failure that's happening out of the front of their house, which they'll be able to see. That is actually contained by the roadway. The water that's appearing at the back of their properties has actually come from the flooding incidents that's some distance away, and the flooding has been caused as a result of overland travel. Now, this is actually a snapshot. This is our worst case scenario. We can actually look at that in time, as we saw in the animation of the model in Conway. So if I play the simulation, you can see time is ticking by up here. The system goes into failure. The road initially accepts most of the flow, but as the extra water comes down the street, it is diverted, and it actually then ends up travelling overland, and as we saw in the worst case scenario snapshot, eventually ends up ponding at this particular property here. Now, the coloration on these triangles, the light colour blue and the dark colour blue, is a representation of depths on the catchment. So the deeper the colour blue, the deeper the water on the catchment itself. So if we just pause the replay there, we can zoom in and we can actually look at that in quite some detail. So we can now see all of the triangles that are making up the 2D mesh. We can see how the triangles are actually going round the properties to make sure our mesh completely butts up to the properties on the model. These properties have come from GIS, so they've come straight in from there. And we can see here we've got each of these triangles in the darker blue colour. There's a higher depth of flooding here than there is here. We can report on those depths in each one of those elements, and really the magic number that we're usually looking at is a depth of around about 300 millimetres. That's the depth at which the water is likely to start to ingress the buildings. It's the depth at which air bricks are typically found, or indeed where the property thresholds are, where the doorways are. And if water can get over those, and then they will have then internal property flooding, which is a degree more serious than just flooding against the outside of buildings and outside of properties. So we've changed from our original approach that we've been doing for many, many years, where we've just been using our models to identify where the failure points are. We now can take a step forward from there and say, yes, we know where the failure points are, we know where the incidents start to occur, but we can also see where the end of that incident is. We can see where the water has travelled and where the impacts are actually happening in the urban environment on properties or potentially on people as well. So that is our classic 1D, 2D urban model of our systems. Now if we can model urban environments with this degree of reliability and complexity, then perhaps we can do the same in rural environments. And so you'll note here that I'm not closing the software in any way. All I'm doing is changing my data selection on my database here. And in fact what I'm going to do now is show you within InfoWorks ICM a river system. Now this is a 1D river model, so this is a complete match with what we would traditionally have been doing with products like ISIS, now called Flood Modeler Pro, or products like Mike 11. Okay, they are one-dimensional river models. We create these models in a very similar way in InfoWorks ICM. We take a very similar build approach to the techniques we use for our drainage systems, but we can build a model in exactly the same way of the river system. So our rivers will typically be built by having a centre line representing the middle of the river as it runs through the catchment, but instead of having manholes, what we will have will be cross sections. And these cross sections will essentially determine the shape of the river at that particular point, both for, in this case, because it's a 1D model, both for the river channel and also for the floodplain. And typically these cross sections will be at 90 degrees to the expected direction of flow. So the river is expected to flow along here, so we can see the sections are at 90 degrees to it there. But if we have flooding on the floodplain, that's typically expected to go in this direction here, so hence the direction of those cross sections. These cross sections will come from river surveys, and we can look at those cross sections in detail by simply picking them up and saying, show me that cross section please. There's a small amount of data about the length of that cross section, and then the section data itself can be shown by clicking the little button, and here we now have the data points down that section which we can see, and each one of those data points will move starting on the left hand side, moving over to the right hand side. So we'll over here on the floodplain to start with, we can see the red line moving as we go down the list, and eventually we will end up over here, which is where the river will actually be found. Okay, that is the actual section. That's an individual section. We can do a similar thing for the whole reach. That's all of the sections put together, and the software has the ability to bring all these sections together, look at them all as one, and then look at all the sections down the network. It puts it into this view here. And once we do that, not only do we get the view of the individual sections that make up the whole river reach, but because we're looking at a set of results, we can also see where the water levels are at any particular point. Now here the channel actually splits in two, and we can see the two channels have actually held both the depths in the main channel, but also in the slight floodplain area that's located over here. So all of the individual cross sections have been put together, and here they all are now linked together to make up our river as a whole. Now we can add to our data sets by using other data available from GIS. In this particular case it's LiDAR data. So this is exactly the same data that we would traditionally now use for our 2D modelling, but here we're just using it in a 1D concept because we can still use that data even if we're not mathematically processing it, but we can still use that LiDAR data in order to show us a representation of where the water will be in what is at the moment a 1D only model. So the only place where we have calculations at the moment are on the 1D cross sections. So each one of these sections is producing a hydraulic result. In between those results we have essentially dead space if it's not a 2D model, and this is a 1D model. So that dead space isn't reporting anything. But what we can do in InfoWorks ICM is to provide a special flood theme where the software will interpolate and interpret the gaps, so it has actual proper hydraulic results on these cross sections. In between those cross sections it can use a distance weighting methodology to predict what the likely water depth would be at any other point you choose to look at on that network. And so as the storm goes by, we're about 6 hours into our storm now, the river is starting to fill up, and we're starting to see inundation because the river channel itself is not able to contain all of the water that's flowing. And we are seeing a representation where the predicted water depths are matched against the LiDAR data in order to show us the areas of the model which are full in terms of the river channel and also the floodplain. So this is the classic type of model, as I said, that we were doing with ISIS or Flood Modeler, and it's the classic model that the UK's Environment Agency will accept. What I'm showing you here is that you don't actually have to come out of your traditional urban models and move into a dedicated river model to do this sort of work. You can now do the river modelling all within InfoWorks ICM. So a model which was perhaps traditionally thought of as a sewer model can actually also be used as a river model. Now this is obviously a very simplistic river model, and there's no particular details of structures or anything like that. But what we can do is we can put all those things in. The software is happy to accept things like bridge structures. So if we have a look at the exact same model, but this time it's been improved and it's been given a river as well as a bridge, and the bridge can be found in this area that we can see here. So I'll zoom in and show you the bridge, and I'll put that terrain back on as well, just so we can put stuff into perspective. So we can see where the river channel is here. At the moment we haven't got any of the flood water in, so I'll drag on my flood mapping theme, and that will allow us to add some water to see what's going on. Let's zoom right in on the bridge itself. This is actually the bridge structure. We can see here bridges have not only the structure themselves, but they have something called a contraction reach and an expansion reach, which is a mathematical term that allows us to model the changing hydraulic flow pattern as the water approaches the bridge. The bridge will obviously impact on the flows, and the area over which it impacts, both as the water approaches the bridge and indeed as it leaves and goes out the other side, is called the contraction zone and the expansion zone. And that's what we can see here, and that's how we represent those visually within the software. But I think you'll all agree that that's not a particularly easy visual picture to understand. Maybe for the modeler or for the engineer, yes, but perhaps not for the general public, particularly if we're producing these models for a court case, and we need to be able to show the general public what is happening and what's going on. So within InfoWorks ICM, we've taken our traditional 3D view, which we've in the past used to look at 3D views of our manholes under the ground, and what we can do is use that same view, but now in our urban environment, and we can start to produce a picture that looks a little bit like this. And this is our river system. So here is our river system, here is our ground, and here is our bridge, and we can see here the water in the main channel. I've just exaggerated the vertical a little bit to make it show up a bit better, but we can see here our bridge, we can see what's going on, and we can essentially fly around our model in 3 dimensions. And the software has essentially rendered this picture for us to show us what is going on in our river, to show us exactly where our bridge is, where the water is, where the deck of the road is, and essentially how that bridge goes right across the river floodplain. And for those of you who are online gamers, this will be sort of classic. It's the sort of Minecraft type view almost of our system, where we can very easily see where our structures are, where our above ground structures are, and we can look at them in 3D. And you will agree that if this sort of picture or this sort of image is put in front of a judge or put in front of a jury, they will understand the model, they will understand where the water is, where the areas of inundation are, where the areas that are safe are, and they will understand how structures like bridges and overpasses are affecting the flows. So we have to step up a gear when it comes to our above ground modelling, because it's very visual, and people see these sort of pictures on the news, and they need to be able to see how that relates to the mathematical models that are produced. So that was all within InfoWorks ICM, but that is a 1D river model. But we have 2D, and so we want to be able to utilize that 2D capability, and we want to be able to look at the overland flows, so floodplain flows, in a lot more detail if we can. So let me show you a 4th example now, which is exactly that. And this is a model that's actually created to look at the potential impact of a reservoir failure. So the dam protecting the reservoir, we need to understand what happens should that fail. And this is the type of study that's been done in the UK quite recently, as commissioned by the Environment Agency, and they basically have had to go around and look at all of their structures and the potential impact. So in this particular model, this is a classic model dominated by 2D. There is a small 1D component just representing the reservoir, which is found in the picture up at the top here, but the bulk of the model, so everywhere from here all the way down the valley and the entire township, is covered by a very detailed 2D mesh. And we use that mesh to understand with great confidence where the water will go should there ever be a catastrophic failure of this reservoir. Now, I would stress at this particular point, this reservoir has not failed, and there's never any indication that it will in the future, but nevertheless we need to understand what might happen should that type of catastrophic event occur. So I can play my hydraulic simulation as I did before. My reservoir is assumed to fail. As a result of that, the content of the reservoir, all the water will run down the valley until it reaches the base of the valley, and then the water will spread out over the urban environment that is lower down. And what we can see is very clearly and very accurately precisely where the water will go. You'll see that the little triangles that we saw in that urban model earlier, the one in North London, they're not visible, and that's because we're using a really small mesh, very, very small triangles, because we need to understand with great detail where the water is going. So it's a very visual picture to see what's happening. Now, why do we produce these models? Well, first of all, we need to understand where the impacts will be. But secondly, it may not just be a flooding event that we're looking at. In this case, it's an inundation event, which in this case is caused by a reservoir, but this could be caused by a breach out of a sea wall as well, a very similar type of approach. And what we need to understand is the properties that are at risk, the areas of the catchment that are at risk, because our emergency planners need to know where they should be directing their attention should this type of event happen. And what this model is showing us very clearly is that anybody living up here is absolutely fine. They are not going to be impacted should that reservoir fail. Our emergency planners and our emergency responders need to deal with people living in this part of the catchment and living down here, and their efforts would be to get the people from this area to the north. Once they're in that area, they will be safe, which isn't a very long distance to travel. So the effort really would just be in moving people from one part of the catchment to the other, not necessarily moving them hundreds of miles away to safety. The other aspect that's very, very interesting is the part that this particular property in the middle of the screen plays if that reservoir should fail, because it actually acts as a flow diversion. Water hitting that property will actually be diverted around that property, and it's actually that property is pushing the flows first of all to the south, but also to the southwest, and in fact acts as a unintended perhaps protection device for the properties located here. As a result of that building, these properties are not going to experience the bow wave of water that came running down the hillside here, and as a result they actually stay dry. It's really these people here and these people here where we need to act quickly. We also have an indication of the sort of time that we have to react. In this case we have around 20 or 30 minutes to put our emergency plan into operation, and this is really an indication of where modelling is going next. It's actually not necessarily looking at what has happened in the past or perhaps what might happen in the future, but they're being used to predict with a great degree of confidence what is going to happen in the future, just a few hours perhaps ahead. And so we are actually moving into the realms of live modelling and being able to constantly run our models all of the time, 24 hours a day, 7 days a week, and constantly have that short-term look ahead, just a few hours look ahead as to where we are and what we have. And that short-term look ahead is very confident look ahead, and we can use the results of that to essentially activate our emergency planning and put things into progress in order to react to an event before it happens and to move people to safety. And in this particular case we have a reaction time. We have to have ourselves at least 20 or 30 minutes of time to know that the event is about to strike, and then we can take action and we can safely move people away. And that's really what these type of models have been used for now. They're moving very much into the live modelling environment. I want to finish up today by showing you something that's perhaps a little bit different. I always like it when I'm presented with models that are completely different, where somebody is really pushing the envelope a little bit and really innovating and thinking about what they can do with the software that we have. What we have here is an example that was provided me by the modelling group located at Atkins in Derby, so my thanks to them. And this is something they looked at, a technique, a modelling technique which has typically been done with full CFD modelling in the past. But here they thought they would look to see if they could actually do that modelling within InfoWorks, using the 1D, 2D mathematics that they know and they trust. And so this is a model of a storage chamber. The storage chamber is fed by a single incoming pipe. Itself is actually a channel, and there's actually a circular bottom to that channel. It's not a flat bottom channel, so it's got a circular bottom. The chamber itself is here, and we can see we have some monitor points, which are these little stars that we can see in the chamber, and the water comes into the chamber and then is directed out of the chamber, controlled out of the chamber by these baffles that we can see here. So we've got 1, 2, 3, 4, 5 baffles in the system, and the baffles direct the flow here through a control device and then out of that particular storage chamber. There's also over here a high level relief. Now I can describe that to you, and you can see the now familiar, I hope, web spider web of mesh that's been created, but the data for this particular device actually came out of an AutoCAD drawing. So all the structure shape has come out, and it's come in, and all of the different devices and the different shapes and all the lines are used to create the structure. Now the engineers amongst you will perhaps look at that and understand what you're looking at, but again, would the general public? So we could use our 3D tool that we used before to look at our bridge, or which we've perhaps in the past used to look at our manholes, and here we can use to look at a structure. In this particular case, the overflow chamber is what we're representing. So here is our incoming channel, and here is the circular bottom that I described to you, that we can see here, represented by the very detailed 2D mesh giving us all the surface types. And then we come into the chamber itself, and we can see the 1, 2, 3, 4, 5 baffles that are directing the flow through these channels that we have here, so creating the 4 channels. And then finally we have the high level weir here, which allows the water to go into that particular shape there. Once water has been directed by the baffles, it comes out and it's picked up by these control devices, which themselves then feed into this pipework and take the water away. We have an emergency sluice over here, which will allow the water out here, and we have an outflow from our chamber as well. So this is really not at all your standard type of modelling that you might expect in the software, but this is a very good example of an organisation who have a number of InfoWorks licenses, thinking a bit outside the box and saying, what else can we do with those models? How else can we deploy them? What else can we use them for? How can we extract even better value from the software? And I think this is a really good example. One of the extra things I want to show you with this particular example is the way you can experiment with the software, and I'll finish with this today by saying this is the base model, but we actually have scenarios. This is a standard feature of InfoWorks, and we will use scenarios typically to look at different networks and different network configurations, but here we are using it to look at different configurations within this particular storage chamber. So here I've just changed the scenario. I've added essentially a couple of training walls, and these training walls come in and will direct the flow. And once we've added those in, we can again put our 3D view back, and we can see exactly where they're located in the structure, and we can see how they will direct the flow left and right once it enters the main chamber, and therefore give better hydraulic performance across all of those different baffles. So that's again just a nice way of showing you this scenario modelling where nothing has changed apart from these baffles, and we can see the different things that they tried, different positions, different ways of essentially optimizing the flow regime in that particular model. So that really finishes the presentation I wanted to make for you today, and really gives you a good idea of what's happening. And for the last 20 minutes we have been using the software live. So I hope you enjoyed that presentation of InfoWorks ICM, and indeed my thanks to all of the organisations who provided the example models that we've been looking at today.